Hey, welcome back. The two problems that we've done so far in this series was the first one is a bit of a review. We figured out the reactions for this particular beam and drew the free body diagram. So if you missed that one, I'm going to throw the card up here. You can go back and pick up those deliberate calculations if you need that. If not, they're shown here. So that may be sufficient. We're not going to go back over and do that again. And then we went on and we did the shear force and bending moment diagrams. We did that with the deliberate method. And so that's a really useful skill set, absolutely essential to understand. So I will put a card up here. If you didn't see that one, you probably want to do that. You probably want to do it first before we do this. Now, that being said, as important as that deliberate method is, in most beam situations with fairly simplified loading, it's possible to use the graphical method, and the relationships between the free body diagram, the shear force diagram, and the bending moment diagram in order to very quickly draw the shear force and bending moment diagrams to get the information we need to go on and do other calculations. And so we want to have those skills. We want to build them up and be able to apply them fairly quickly so that we can be efficient in everything we do. We're going to start off, and that's exactly what we're going to do, is we're going to redo the shear force and bending moment diagrams that we covered in the last problem, only we're going to use the graphical method. And I'll take the time as we're going along to explain the relationships as we're going down from one diagram to the next. And as we go on to problems coming up, you'll see that we do it all the time, and we'll start to do it faster and faster and faster without the detailed explanation. Let's get started. So we've got the free body diagram, we have the reactions, and we need to do the shear force diagram. So the shear force diagram, of course, we're looking for forces and their impacts going in that y direction, or parallel to the cross-sectional face, if you will. So where there is a force on the free body diagram, or the load intensity diagram, if you will, that causes a change in the shear force diagram. If it's a point load, it causes a discontinuity or an immediate change in the shear force diagram equal to the magnitude of the point load. If it's a uniformly distributed load, well, we'll get to that. We've got that coming up. We'll do a couple of those, so I'm not going to get you too distracted with it right now. If we're starting at 0, we're working our way left to right across our shear force diagram, and we're graphing the internal shear force in our beam. So as we said, the point load, or in this case, the reaction AY, causes an immediate change in the shear force diagram, which starts at 0 because we're at a pin end, and it's going to cause the shear force diagram to increase by its magnitude. So it has a magnitude of 133.3. And so it's going to push, if you will, the shear force diagram up equal to its value of 133.3. Now, as we're moving left to right between point A and a point of point load application in the middle, there is no vertical forces being applied at all. And so there will be no change in the shear force diagram. So it's going to be constant going across until we get to that point load. Now, we already talked about what happens at a point load. Of course, it is a discontinuity in the shear force diagram equal to the magnitude of the point load. So we take our 133.3, we subtract our 200 kilonewtons from it, and we get a value of minus 66.7 kilonewtons. And so to draw that in, it goes down to minus 66.7. Once again, there are no vertical forces applied between the point load and point B, so there will be no change in the shear force diagram. And we will draw it across, at which point RBY will cause it to return to 0. Really important for our shear force bending moment diagrams to start and end at 0. And so if it had finished somewhere else, we would be a good indicator to us that we had made a mistake along the way, and we should go back and look at it. But in this case, we seem to be pretty happy. And so we've done our shear force diagram. And of course, what this is telling us is we can choose any point X along the beam and go to this and read off the value of the shear force in the beam at that point, which is going to be really useful when it comes to designing the beam itself. Now, to get to the bending moment diagram, what we need to do is we need to use the relationships between the shear force diagram and the bending moment diagram to very quickly draw that graph. And so there's a couple bits of information which will be useful to us. So I'm just going to go up here and I'm going to calculate the area in each of these sections on our shear force diagram. So in the first one, so area is equal to, and of course the value is 133.3 multiplied by the 1 meter, and we have an area of 133.3. That would be kilonewton meters because it's kilonewtons and meters. And then we'll do the same thing here. And so we have minus 66.7 kilonewtons times 2 meters. Sorry, I'm going to leave the units off just because they're labeled 2 meters. And so that's equal to negative 133.3 kilonewton meters. Now we're ready to look at the bending moment diagram. So there's a couple of relationships that we can use. So the first thing is, of course, we're starting and ending at 0. If there is a point moment, there isn't in this case, that would cause a discontinuity and a jump up or down in the bending moment diagram. Otherwise, what we're looking at is that shear force diagram, and the change in moment from one point to the next is equal to the area under the shear force diagram. And so we know that between 0 at point A and under the point load, we will have a change in moment equal to the area under the shear force diagram. So that's going to take us to a value of 133.3 kilonewton meters on the moment diagram. Now, then the question is how does it get there? Well, the other relationship that we know is that the magnitude of the shear force diagram is equal to the slope of the bending moment diagram. And so we're going to have a positive constant slope. It's a constant magnitude in the shear force diagram, so we'll have a positive constant slope in the bending moment diagram equal to 133.3. And so where we have constant shear force diagram, we have a linear bending moment diagram. We do the same thing from the point load over to point B, and it is a constant negative slope of 66.7. So we get a change in our bending moment diagram of negative 133.3, which takes us right back down to 0. Something weird's going on with my screen there. Now, we can certainly go ahead and figure out what our equations are for these lines if we wanted to. Of course, as we just talked about, they're straight lines, so we can use the y equals mx plus b configuration. We know the slope value is equal to the value off the shear force diagram. But I'm happy with what we've done so far, and I think I'm just going to leave it there. So the one thing I want to do is I do want to introduce a problem where we have a uniformly distributed load, because it just complicates things just ever so slightly. The relationships are the same, but of course we're going to have to deal with them. So I'm going to close this off. I'll leave you a link to the next video, and we're just going to do a simply supported beam with a uniformly distributed load on it and use the graphical method to generate the shear force and bending moment diagram. So I hope to see you out for that one.